Hello and welcome to this presentation related to Bernoulli's equation. Bernoulli's equation essentially applies the principle of conservation of energy to hydraulic systems. For your reference, there are 3 previous presentations that contain underpinning knowledge related to this current presentation. The first presentation relates to hydrostatics, an introduction. Here we outline basic terminology, definitions and formulae associated with hydrostatics. For example, the formula for calculating the pressure in a fluid in a closed container when subject to an external force. And also we highlight the various densities, mass density, relative density and specific weight or weight density. The second presentation continues with hydrostatics, but this time considers pressure due to the self-weight of a fluid. Pressure P is equal to rho GH formula. And the third presentation relates to the principle of continuity. Here we consider flows through horizontal, diverging or converging pipes, calculate the volumetric flow rate, calculate the mass flow rate. So as I say, it's strongly encouraged that you review the 3 previous presentations before considering the contents of this presentation. And here's the presentation overview. We commence with an introduction related to fluids in motion. We next consider properties of fluids, that is compressibility considerations, friction, rate of flow. Then we consider energy in fluid flow, pressure energy, kinetic energy, potential energy. Then Bernoulli's equation, firstly with no friction considerations. The Bernoulli's equation shown above, where we have pressure energy, kinetic energy, potential energy, inlet and outlet. Then exercise 1 is an application of Bernoulli's equation with no friction consideration. Next, Bernoulli's equation, this time with friction head considerations. So we add this friction head term into the equation. And exercise 2 is an application of Bernoulli's equation to find, in this particular exercise, the head loss. We then have the continuity equation. This is essentially an overview of the previous presentation, which is strongly encouraged you view before reviewing this presentation. And exercise 3 is a brief application of continuity. Here's the continuity equation related to flow through circular section pipes. And finally, we have some tutorial questions for you to attempt at your own pace. And these questions involve using Bernoulli's equation and the continuity equation. And for your reference, here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times stated are rounded to the nearest minute. And for your further reference, here are the start times related to the questions contained within the presentation with fully worked solutions. So question 1A, question 2A, question 3A, and here's the start time to the worked solution to question 4A. There's various terminology used within this field of study. You'll hear the term fluid mechanics used, so as defined here, hydrodynamics, as defined here, and the term hydraulics, which I will predominantly use throughout the presentation. Hydraulics, which is actually the Greek word for water, is a system operated by or involving water or some other fluid, such as oil, under pressure. Fluids in motion, an overview. Let's consider hydraulic systems and the principle of conservation of energy. We define a hydraulic system as one that performs and functions tasks using a pressurized fluid. In any hydraulic system, there is a continual variation in the conditions of flow. A system or pipeline can have the following characteristics: change in diameter. So pipes may increase in diameter with a consequent reduction in velocity and a corresponding reduction in kinetic energy. Or a pipeline, for example water, oil or gas pipelines, may be laid over undulating country where fluid may travel up an incline with a consequent increase in potential energy. Although variation of individual energies is continually occurring, there is a definite relationship between them. This relationship is expressed by Bernoulli's equation. Bernoulli's equation essentially applies the principle of conservation of energy to hydraulic systems. Hydraulic systems and friction losses. Loss of energy does occur within hydraulic systems due to the friction between the containing pipe or channel and the flowing liquid. Other losses can occur due to poor pipe design, for example where sudden enlargements or contractions occur, and the viscosity of a fluid. Viscosity is the measure of resistance of the molecular bonds to shearing effects within fluid flow. Hydraulic systems and friction losses continued. Friction losses also occur due to the type of fluid flow, of which there are two types. The first type is streamline or laminar flow. This occurs when the velocity and pressure in a fluid being a liquid or gas, at any cross-section of the pipe through which it is flowing, remains constant over a long period of time, as indicated in Figure 1, shown here. This illustrates streamline laminar flow. There is no mixing of the layers, no turbulence, and no fluctuations in velocity of the fluid particles, thus producing continuous flow without sudden changes. The second type of flow is termed turbulent flow, and this occurs where the fluid undergoes irregular fluctuations or mixing. In turbulent flow, the fluid's velocity at a point is continuously undergoing changes in magnitude and direction, as indicated in Figure 2. This indicates turbulent flow. Let's consider properties related to fluids. Before considering the various types of energy, it is useful to consider the various properties related to fluids. Compressible fluids. Liquids and gases are included in the collective term fluids. It is generally accepted that when subject to compressive forces, 1. Gases undergo significant reduction in volume, i.e. are compressible, whilst 2. Volumes of liquids remain almost unaltered, so liquids are deemed incompressible. Friction. When liquids flow through a pipe, the motion is resisted by friction. Losses due to friction may be calculated, although such calculations will not be considered at this stage of the presentation. Within these notes, the effect of losses will be considered only in their overall effect, and often the effect of friction will be considered negligible and so ignored. Let's consider the velocity of a fluid, symbol lowercase v. This is the liquid's velocity passing a particular pipe cross-section. The SI unit of velocity is the meter per second, also written as the meter second to the -1. And the velocity used within our calculations will be the average velocity of flow. It should be noted that the velocity of flow over a pipe cross-section, as shown in Figure 3 of the velocity profile here, varies from a maximum at the centre of the cross-section to a minimum where the liquid is in contact with the pipe. This is due to the friction between the liquid and the pipe. We have the maximum velocity shown here at the centre of the pipe. Our pipe is of diameter d, and we have 0 velocity at the wall due to the friction between the liquid and the pipe. And here's the location of the mean velocity, also termed the average velocity, that will be used within the following calculations. Let's consider rate of flow. The rate of flow is a phrase often used rather loosely by engineers, and so to avoid confusion, below are stated two types of flow rate referred to within this work. First is volume or volumetric flow rate, usually given the symbol capital Q with a dot above the Q to indicate a rate of flow. And volumetric flow rate is the volume of fluid flowing in unit time past a particular pipe cross-section. The SI unit of volumetric flow rate is meter cubed per second, or of course written as meter cubed second to the -1. Rate 2 is the mass flow rate, symbol m dot. This is the mass of the fluid flowing in unit time past a particular pipe cross-section. the SI unit of mass flow rate is the kilogram per second or kilogram seconds -1. Fluids in motion. Any fluid in motion contains three basic forms of energy by virtue of its 1. Pressure and density, this is termed pressure energy, 2. Velocity, this is termed kinetic energy, and 3. Its position relative to a defined datum, that's termed potential energy. Let's now consider pressure energy, also termed flow work energy. Consider an incoming fluid. If flow of liquid between locations x and y, see figure 4 on the right hand side here, here's x and here's y, has a total volume V1, then for flow to occur, this volume must be replaced by an equal volume entering from outside of the system. If pressure in the fluid is P1, then work done on the fluid inside the system by incoming fluid equals force F multiplied by distance S that the fluid is displaced. Note that force is equal to pressure multiplied by the cross-sectional area of our pipe, so that's P1 multiplied by A1 at section 1. So the work done can be written as the force from above P1A1 multiplied by distance S. But note that A1S is actually volume displaced, labelled V1 here. So we can write the work done on the system is P1 multiplied by V1. This increases the energy level of the system by P1, V1. Pressure energy or flow work energy continued. Consider the outgoing fluid. Similarly, fluid leaving the system will do work equal to P2, V2 on the surroundings. The outgoing fluid reduces energy in the system by the amount P2, V2, where P2 and V2 represent respectively the pressure and volume and the exit from the system. The mass of fluid occupying volume V1 is M1 and the mass of fluid occupying volume V2 is M2. Notice that the density of the fluid, Greek symbol lowercase rho, is stated as rho is equal to M1 divided by V1, and that's equal to M2 divided by V2. Transposing the density equation to make volume the subject gives V is equal to M divided by rho. So from our previous slide, work done on the system, instead of being written as P1 multiplied by V1, can be written as P1 multiplied by M1 divided by rho. And that equals to P2 multiplied by M2 divided by rho. Hence, at point 1 in the system, the specific pressure energy is equal to P1 divided by rho. In other words, we divided the work done on the system in this line by mass to determine the specific pressure energy here. And of course, at point 2 in the system, the specific pressure energy is P2 divided by rho. The term specific energy means the energy per unit mass of fluid. The SI unit for specific pressure energy is the joule per kilogram or joule kilogram -1. Fluids in motion continued. Kinetic energy, if mass m of a fluid has linear velocity v, then the fluid kinetic energy is a half mv squared. For unit mass of fluid, the specific kinetic energy is written as a half v squared, again having the SI unit of the joule per kilogram. Potential energy, if mass m of a fluid is stored at height h above a defined datum, then the potential energy in the fluid equals to mgh, mass times gravitational acceleration times the height, or for a unit mass of fluid, the specific potential energy is simply gh, SI unit joule per kilogram. And purely for reference, the unit of the joule per kilogram, when derived in base SI units, can be shown to be the meter per second all squared. Let's now consider Bernoulli's equation. The diagram on the right hand side shows a hydraulic system having fluid in at position 1 here. We have a pressure P1 in the fluid and a velocity V1, and we have fluid out at position 2 here, where we have pressure P2 in the fluid and velocity V2. Notice the heights are measured from the datum shown here. This is height H1, this is height H2. So let unit mass of fluid flow at a steady rate through the system shown in figure 5 above, applying the principle of conservation of energy, in other words specific energy in the fluid entering the system, position 1, is equal to the specific energy in the fluid leaving the system, position 2. Bernoulli's equation continued, just repeated figure 5 for convenience here. So fluid energy is on entering at position 1. Here we have specific pressure energy, that's P1 upon rho, added to specific kinetic energy, that's V1 squared divided by 2, added to specific potential energy, that's GH1. So we're simply adding these energy terms together on the left hand side. So applying the principle of conservation of energy, the fluid energies on entering the system must equal the fluid energies on exiting the system at position or location 2 shown here. So the input energy is equal to the output energies of specific pressure energy, P2 upon rho, added to specific kinetic energy, V2 squared divided by 2, added to specific potential energy, GH2. So again, we add the energy terms on the right hand side and they equal to the energy terms on the left hand side. Bernoulli's equation continued. So therefore P1 upon rho plus V1 squared divided by 2 plus GH1 is equal to P2 divided by rho plus V2 squared divided by 2 plus GH2. And that equals to a constant for the principle of conservation of energy. If we now divide both sides of the equation by gravitational acceleration g, this produces what is known as Bernoulli's equation, stated in terms of head of liquid. There are various forms of Bernoulli's equation, and if you review other sources, they may show you a different form. What's shown in the bolded box here is the Bernoulli's equation format we will use within this presentation. So note that each quantity in the above Bernoulli's equation is measured in terms of head of liquid. So note the SI unit for each of the quantities in the above Bernoulli's equation is the meter. And for reference, there are benefits of Bernoulli's equation being written in terms of fluid head. Firstly, the equation is dimensionally homogeneous, so every term in the equation has a unit of length. So this has the SI unit of the meter, or the imperial unit of the foot. 2. The head of fluid is independent of density. The same pipe with the same flow rate has the same loss, irrespective of the fluid, whether the fluid's water or oil that's used. Engineers tend to design systems in terms of head of fluid, only converting to pressure when needed, sometimes at the end of the calculations. Third reason, pump performance is expressed in terms of head. Pumps add energy per unit weight to a system, and knowing the head losses allows choice of pump to match losses. Just typical diagrams here showing the head, in this case capital H, plotted against flow rate capital Q in meters cubed per second. Friction losses within our system are represented by a head loss, labelled as HF. Benefits of Bernoulli's equation written in terms of fluid head continued. And 4. Using head offers physical intuition as a visual representation. So a friction loss stated as 4 meters is more intuitive to visualize than a friction loss stated as, say, 39.2 kilopascals, as is illustrated in the diagrams below. On the right hand side we have pressure head, elevation head, that's our height above a datum, Z, and velocity head, and also shown here what's termed head loss due to friction effects. For example, in this illustration here, it shows a 30 feet theoretical head from the pump, but friction in the pipe causes head loss. 28 feet is maximum delivered. So you'll see in a moment that we will consider frictional losses in pipe systems by including the term HF for friction loss related to head of fluid. And this slide is purely for reference only, where if you want to calculate the friction of fluids flowing through a pipe, we can refer to the Moody chart, diagrammatically shown below, to help us calculate losses in terms of head for the fluid flowing through a pipe. And again, for reference on this slide, it shows losses due to flow through pipe fittings, such as various elbows, valves, etc. Again, we can work out a head loss to use in Bernoulli's equation. But as I say, this is slightly beyond the specific scope of this current presentation. Let's now apply Bernoulli's equation to a hydraulic problem. Exercise 1. Water enters a pipeline with a pressure of 2 bar and a velocity of 5 meters per second. So we have the pressure P1 and the velocity V1. That's section 1. If the pressure of the water 25 meters below the entry point is 1.2 bar, so we know the pressure P2 here at location 2, we've got to calculate the velocity at station 2. So we need to try and find V2. We can assume the density of water to be 1000 kilograms per meter cubed, but we would assume that anyway, even if not stated. The answer for the outlet velocity is 26 meters per second. So let's now apply Bernoulli's equation to solve this problem. So exercise 1, the solution. As with all problems, let's read the question carefully, extract the information from the question, let's state it using appropriate symbols and appropriate units, and then apply the appropriate equation. So taking the information from the question, we're given P1, 2 bar, converted that straight away into pascals, so that's 2 times 10 to the 5 pascals, or 0.2 megapascals. And the velocity in that is 5 meters per second, so V1 is 5 meters per second. We're told in the question that the outlet is 25 meters below the entry point, so if we consider our datum at the lowest point of the system, which we generally do with energy type problems, purely for convenience of numerical calculations, in this case the height H1 would be 25 meters, given the density of water in the question. So that's all the properties for our inlet to the system. Now considering the outlet, the outlet pressure is 1.2 bar, so P2 here converted the 1.2 bar into pascals, of 1.2 times 10 to the 5 pascals, or 0.12 megapascals. So we know pressure P2, but we have to calculate the outlet velocity, so V2 is unknown. If we consider our datum to be the lowest point in the system, then H2 in our case would be 0. And just note for reference, I've calculated the specific weight of the water, that's rho G, shown here. That's just for convenience of later calculations. So that's the information extracted from the question. Let's now apply Bernoulli's equation and try and solve for the outlet velocity V2. Exercise 1, solution continued. I've just stated this information from the previous slide for convenience. So here's Bernoulli's equation applied, ignoring frictional losses in this particular instance. So here's the formula, P1 upon rho G plus V1 squared divided by 2G plus H1. And here are the numerical values subtracted from above. And that's equal to the P2 upon rho G plus V2 squared upon 2G plus H2. And again, the information inserted into the equation extracted from above. The next line just shows all the terms being evaluated. I'll let you review the number crunching at your own pace. On the right hand side here, we have the unknown V2, essentially V2 squared at the moment. Exercise 1, solution continued. Just repeated this line for convenience from the previous slide. So now rearranging, I've summed the left hand side, shown here. I've subtracted the right hand side, and I multiplied throughout by the 19.62. So that left me with V2 squared, and simply evaluating V2, it's 26 meters per second to two significant figures. Again, I'll let you review the calculations there. So that's applied Bernoulli's equation to a problem where frictional effects were not considered, where we needed to calculate the output velocity given all relevant information using Bernoulli's equation. And if of interest, here's exercise 1, the classroom solution worked through with the students. In this solution we actually transpose the equation to make V2 the subject and then inserted the appropriate values. As I say, just an alternative approach to the solution. Let's now consider frictional resistance to flow. The Bernoulli's equation assumes that there is no frictional resistance to the flow, but in practice frictional resistance to flow is always present and reduces the available energy in the fluid at the exit from the system. In other words, specific energy in the fluid entering the system is equal to the specific energy in the fluid leaving the system, plus the specific energy to overcome frictional resistance to the flow. Let's let HF be the frictional resistance in terms of head, meters. So now Bernoulli's equation can be modified to include friction losses. So basically the same equation as before, except now we add the HF term on the right hand side. That's how we're going to account for frictional losses at this level of our study within this presentation. Frictional resistance to flow continued. So note from the above equation, it is seen that friction affects the system's energy balance, but not the mass balance. Refer to the continuity principle of our previous presentation. So friction causes an energy drop between inlet and outlet, which is usually associated with a pressure drop. Calculation of power required to overcome friction. Power is equal to mass flow rate, m dot, kilograms per second, multiplied by gravitational acceleration, g, multiplied by the frictional head, hf. Just note for reference, from our previous work, m dot is mass density multiplied by volumetric flow rate, q dot, and volumetric flow rate as the unit of the meter cube per second, and the mass density of the fluid as the unit of the kilogram per meter cubed. Let's now apply Bernoulli's equation accounting for frictional losses within exercise 2. So water having a relative density of 1 enters a horizontal pipeline with a pressure and velocity of 2 meganewtons per meter squared and 7.5 meters per second respectively. The water leaves the system with a pressure of 1.65 meganewtons per meter squared and velocity of 25 meters per second. We have to determine the loss of head due to frictional resistance. Answer is given as 6.7 meters to 1 decimal place. Just repeated Bernoulli's equation here, accounting for friction losses, HF. The solution essentially takes the format of that for exercise 1. The only difference here is that we have to find the unknown frictional resistance, HF, but the approach is very similar, extracting information from the question, stating appropriate symbols and units, inserting the values into the equation and rearranging in this case for HF. I'd encourage you to start the presentation and attempt exercise 2, but I will show you the full work solution on the following slides. Exercise 2, commencement of the solution, states in the question this is a horizontal pipe, so what's shown in my sketch here, so obviously there'll be no height differential between the inlet and the outlet. To extract the information from the question, inlet pressure is 2 meganewtons per meter squared, that's 2 times 10 to the 6 pascals. Inlet velocity, V1, 7.5 meters per second. As I said, the height differential is 0 here, so H1 will leave as 0. Note, water has the relative density of 1, stated in the question here, so that's my lowercase sigma equals to 1 for relative density. So our mass density would be 1000 kilograms per meter cubed. Our previous work converting from relative density to mass density. And again, for later convenience, I've worked out the specific weight, which is 9,810 newtons per meter cubed. So that's my inlet properties, P1, V1. On the outlet, P2 is 1.65 meganewtons per meter squared, or 1.65 times 10 to the 6 pascals. The outlet velocity, V2, is given as 25 meters per second, and of course H2 is 0 because it's a horizontal pipe. So now we have the outlet properties of P2, V2. The question wants us to find HF. the loss of head due to frictional resistance. So now we're just going to put these values into the Bernoulli's equation, counting for friction effects, and rearrange for HF. Solution continued. Just repeated this information from the previous slide purely for convenience. So here's our Bernoulli's equation, but this time including frictional losses. So on the left hand side we have our energy terms at inlet, position 1, and on the right hand side we have our energy terms at the outlet, position 2. And of course now accounting for the frictional effects. Our next line will simply insert the values from above with appropriate terms. Again, I'll let you review this at your own pace. Notice that H1 is 0, horizontal pipe here, so of course H2 will be 0. And the only unknown is HF, so we're going to rearrange the equation for HF. I'll let you review the calculations at your own pace, but the frictional loss in terms of height HF is approximately 6.7 meters to 1 decimal place. And here's exercise 2, alternative approach, based on the classroom solution worked through with the students. And again, we initially considered Bernoulli's equation, eliminated the terms that are not relevant in this question, which was the height terms H1 and H2. And then again, we rearranged the equation algebraically and inserted the values to find the friction head. Power available, this time accounting for friction effects. So to the above shown scenario, to calculate the available power at the nozzle outlet, position 2 here, the power is equal to the mass flow rate m dot multiplied by gravitational acceleration multiplied by, in bracket, by h shown here, minus hf. As stated at the beginning of the presentation, there is a separate presentation related to continuity and the continuity equation. I have shown the theory here again for recap, but I'm going to let you review this at your own pace because it's strongly encouraged that you have seen the previous presentation, but should you want a brief overview, this is how the continuity equation is derived, accounting for, in this case, a converging pipe between position 1 and position 2. Continuity equation continued. Applying the principle of conservation of mass, we assume that the mass of the fluid passing section 1 per unit time, shown here, is the same as the mass of fluid passing section 2 per unit time, shown here. Note that the conservation of mass principle is not affected by pipe friction. Continuity equation continued, and again I'll let you review the slide at your own pace here, but we can show that the volumetric flow rate Q dot is AV, cross-section area times velocity at that section. Continuity equation continued, again I'll let you review the derivation at your own pace, and finally for a circular cross-section, having diameter at the inlet d1 and outlet d2, the continuity equation is d1 squared multiplied by v1 is equal to d2 squared multiplied by v2. Again, for your reference, there is a separate presentation related to the application of the continuity equation. Here's exercise 3, application of the continuity equation for reference. At a section in a tapered pipe, the inlet diameter is 0.7 meters and the velocity of the liquid is 5 meters per second. Assuming the flow of the fluid is to be steady, laminar flow, we've got to determine the velocity at the outlet when the pipe diameter is 0.5 meters. We're given the outlet velocity here. So essentially we need to apply this equation for continuity between the inlet and the outlet. I would encourage you to stop the presentation and try and determine the velocity at the outlet, V2. The full work solution is shown on the following slide. Here's exercise 3, full work solution. Again, as always, extract the information from the question for the inlet and for the outlet. Noting we have to find the velocity at the outlet. And for circular pipes, we know the continuity equation simplifies to d1 squared multiplied by v1 equals to d2 squared multiplied by v2. In this case, we transpose the equation for v2, then insert the values from above. We can evaluate the velocity of v2. I'll let you review the solution at your own pace. Here's exercise 3, classroom solution with the students. Commencing with the continuity equation, we essentially rearrange the equation for v2. Insert in the values of D1, D2, and velocity V1. Velocity V2 was 9.8 meters per second. Here's application of Bernoulli's and continuity equations. Question labelled 1A here. Oil of density 800 kilograms per meter cubed enters a 500 millimeter diameter pipeline with a velocity of 3 meters per second and a pressure of 4,400 kilopascals and is discharged through an orifice of 150 millimeters in diameter and 30 meters below the entry point. The frictional losses are equivalent to a head of 3.5 meters of the oil. We've got to determine the velocity and pressure of the oil at the point of discharge. It's station 2 in our previous diagrams. The velocity and pressure are shown in the bracket here. In question 2A, water contained in an open tank is discharged to the atmosphere through an orifice 25 millimeters in diameter. If the surface of the water is maintained at a constant 1.6 meters above the center of the orifice and ignoring friction losses, we've got to determine 1. The velocity of the water as it discharged through the orifice, that's at position 2, and 2. The volume of the water flowing in litres per minute. Again, answers shown in the bracket here. I would encourage you to stop the presentation and try and attempt question 1A and 2A. As a hint for question 1A, we firstly need to apply continuity to the information given to find the velocity at the outlet, and then apply Bernoulli's equation to find P2, the pressure at the outlet. In question 2, we need to apply Bernoulli's equation to find the velocity of the water at the outlet. Notice we can ignore friction losses here. So applying Bernoulli's equation, we will find the velocity here. A note for position 1 within our analysis relates to the surface of the water in the tank, and position 2 is the centre of the orifice for the outlet here. So in this case, as position 1 and position 2 relate to atmospheric considerations, they both have a value of 0 gauge pressure, and within question 2A we're informed that there is no movement of the surface water in the tank at position 1. So we'll assume there's no velocity of the fluid at position 1. Of course there will be velocity of the fluid at position 2 as the fluid discharges from the orifice. So in summary, the inlet pressure P1 is 0, the outlet pressure P2 is 0. In this case the inlet velocity V1 will be 0, but the outlet velocity V2 will have a value. And note in this question diameter D1 is not required. And for part 2, knowing the velocity from part 1 and calculating the area of the outlet, we can find the volumetric flow rate through the outlet, station 2, position 2. But notice the answer required is in litres per minute. So I'd encourage you to stop the presentation and attempt questions 1A and 2A, but I will briefly show you the full work solutions on the following slides. So here's question 1A solution. I'll let you review this in detail at your own pace. As always, we should extract the information carefully from the question, state appropriate symbols and appropriate units. I would always encourage you to sketch a diagram showing clearly the inlet, station 1 here, and the outlet, station 2. Notice in this case the inlet is above the outlet, so that's reflected in the height here, h1 of 30 meters and h2 is 0 meters. In this question my datum is essentially the centre of the outlet, station 2. And question 1A solution continued. Here's our continuity equation, q dot 1 equals to q dot 2. As we have circular pipes, we can commence from this equation, derived on our previous slide. We're rearranging for velocity V2, and V2 is calculated here. Question 1A, solution continued. For step 2, we're now applying Bernoulli's equation, and notice we're including frictional losses here. Again, I'll let you review the solution at your own pace, just basically inserting the values from the previous slide. This time we have to rearrange for the pressure at the outlet, P2, it's the only unknown in the problem. So rearranging for P2, we find the pressure is 41.7 bar to 1 decimal place. Here's question 1A. classroom solution worked through with the students. Commence with the continuity equation to find the velocity, and then using Bernoulli's equation we calculated pressure P2. Question 2a, here's the commencement of the solution. For my diagram on the right hand side here, location 1 is the tank, location 2 is the outlet orifice. To my datum is at 2, then H1 is 1.6 meters, H2 is 0. Because both the tank and the orifice are open to the atmosphere, I'm stating that P1 is 0 gauge pressure, P2 0 gauge pressure. I state that V1 is equal to 0 because the flow is from the tank, and we have to find V2, velocity at the orifice. V1 is assumed to be 0, and D2, we're given the diameter in the question. Notice I've converted it to meters here. And we can work out the cross-section area A2 in meters squared. Here's question 2a, solution continued. Firstly, we're considering Bernoulli's equation, but ignoring frictional losses. We've got to find V2, the outlet velocity. For Bernoulli's equation, 3 terms on the left-hand side, and our 3 terms on the right-hand side. As I said, we're ignoring friction effects in this case. From the information given in the question, repeated here for convenience, P1 is 0, so this term's omitted from the equation. V1 is 0, so omit this term. H1 has a value, it's 1.6 meters, so 1.6 meters on the left-hand side of our equation. And the right-hand side values, again repeated here for convenience. P2 is 0 and H2 is 0. So essentially we're left with H1 on the left-hand side is equal to V2 squared divided by 2g on the right-hand side. We know the value of g, it's always 9.81 meters per second squared. So we can now transpose the equation for V2. I'll let you review the transposition at your own pace. You need to make V2 the subject. And we find that V2 is equal to 5.6 meters per second to 1 decimal place. Here's question 2a. This is the classroom solution used with the students. Again, considering Bernoulli's equation, we have H1 on the left hand side and V2 squared divided by 2g on the right hand side. So in this case H1 is equal to V2 squared divided by 2g, but with this solution we've actually transposed the equation for V2 and then inserted the numerical values. So again V2 is equal to 5.6 meters per second. As I say, just a slight variation on the solution. And question 2a, part 2. So flow rate at the outlet Q dot is going to be A2 multiplied by V2, velocity at the outlet. So inserting the values, we calculate Q dot, shown here in meters cubed per second, and I've shown that now converted to meters cubed per minute, basically multiplying by 60, and litres per minute, multiplying by 1,000. So Q dot is approximately 165 litres per minute. And purely for reference, here are the unity brackets related to the conversions on the previous slide associated with question 2a, showing why for the meters cubed per second to meters cubed per minute conversion we have to multiply by 60, and for the meters cubed per minute to the litres per minute conversion we have to multiply by 1,000. For further information there is a separate presentation related to the use of unity brackets. Further tutorial questions, question 3a, question 4a. Question 3a is similar to question 2a. As there is apply Bernoulli's equation, calculate the velocity at the outlet, and then calculate the volumetric flow rate in litres per minute. Just notice it's a horizontal pipe, and you are ignoring losses within the calculations. And then find the volumetric flow rate, answer shown here in the bracket. A further note for question 3a, the velocity is discharged to atmosphere, so that will mean that the gauge pressure at the outlet will be 0. Question 4, we have to find firstly the pressure in the water at the entry to the pipe, that's a pressure equals rho GH formula. Part 2, apply Bernoulli's equation to find the velocity of the water being discharged from the nozzle, station 2. And part 3, we've got to find the velocity in the pipe if now the diameter is 2 meters. Answers to part 1, 2 and 3 shown in the bracket here. As a hint for question 4a, position 1 is located at the inlet, position 2 located at the outlet from the nozzle. I'd encourage you to start the presentation, attempt questions 3a and 4a, but I'll briefly show you the full work solutions on the following slides. And here's the commencement of the solution for question 3a. Considering a horizontal nozzle, the inlet pressure to the nozzle from the seawater is 5 bar. We have negligible velocity, so V1 is equal to 0. Horizontal pipe, so H1 is equal to 0. And we can ignore diameter D1. This particular calculation is not stated and not required. So that's all the inlet properties to our nozzle. Consider the outlet properties. The discharge from the nozzle is to atmosphere, so the outlet pressure P2 is 0 gauge pressure. We're trying to find the velocity outlet horizontal pipe, so H2 is equal to 0, and the diameter at the outlet is given in the question as 20 millimeters, 0.02 meters. The question states the relative density of the seawater, 1.02, converted to mass density here, and also for convenience, a weight density here. Question 3a, solution continued. The top right hand corner here just extracted some values from the previous slide for reference. So applying Bernoulli's equation, ignoring frictional effects. So in this case we do have an initial pressure, P1. We don't have an initial velocity, V1, so this term will be ignored. Because it's horizontal pipe, of course, we want to have a H1, that term is ignored. So just a one term on the left hand side to evaluate. On the right hand side, we don't have a pressure P2, so this term is ignored. We're trying to calculate the velocity V2, so this term is included. And again, of course, the horizontal pipe, so H2 is equal to 0. So on the right hand side, just this term to consider. Evaluating the left hand side, evaluating the denominator on the right hand side, we can then transpose the equation to find V2 by multiplying both sides by 19.62 and then square rooting both sides. The outlet velocity V2 is approximately equal to 31.31 meters per second. That's the four significant figures. Question 3a, solution continued. Part 2, we have to calculate the flow rate, Q dot. To do this, we need to calculate the area of the outlet, station 2 here, and multiply by the velocity at the outlet, V2, which we've calculated on the previous slide. So A2 is calculated from pi d2 squared divided by 4. We're given the diameter in the question. So here's A2 in terms of pi meters squared. If we now multiply the A2 by V2, we can evaluate Q dot, and that's in terms of meters cubed per second. But the question requires us to convert this into litres per minute. So I'm showing the conversion in two stages here. Firstly, converting from meters cubed per second to meters cubed per minute. We multiply by 60. And then converting from meters cubed per minute to litres per minute. We multiply by 1000. Final answer for Q dot is approximately 590 litres per minute. Question 3a, solution continued. Just showing you how to use the unity brackets to help with the conversion of a flow rate in meters cubed per second into litres per minute. Remember with unity brackets, there are counts in unity brackets, so the meters cubed cancelled here, and the seconds cancelled here, to leave us with the unit of litres per minute. That's just for background reference. And just as a contrast, here's question 3a undertaken in the classroom with the students. Just a slightly different approach here, where we initially rearrange the equation algebraically to find V2. We commence by considering Bernoulli's equation. So as shown on the previous slide, we have this term on the left hand side and this term on the right hand side. And all that's happened in the slide below is that we've equated these two terms, cancelled the g's from both sides because common to both denominators, and rearranged for V2. But in the figures we find V2 again, 31.32 meters per second, And then to calculate the flow rate, Q dot, we need to calculate the area of the outlet. We're given the diameter of the outlet, and it's the area at the outlet multiplied by the velocity at the outlet, allows us to calculate the Q dot, again 590 litres per minute. That's just an alternative solution that was undertaken with the students in the classroom. Let's consider the solution to question 4a. Here's the question again for your reference. We'll show the solution on the following slides. Question 4a continued is the beginning of the solution. As always, we extract the information from the question. Notice here we've labelled position 1 as the water pipe inlet, shown here, and position 2 as the water pipe outlet, shown here at the nozzle position. We need to calculate the value of H1, shown here. Notice the datum for our high energy is essentially in the nozzle outlet, position 2. So here's the calculation for H1, essentially using basic trig. We will need to calculate the pressure at P1. That's due to the head of fluid, 30 meters in the tank. We'll calculate that on the following slide. We know that pressure P2 is atmospheric pressure, so that's 0 gauge pressure. Notice in the question, the density of water is given as 1 megagram per meter cubed. 1 megagram per meter cubed is actually a mass density of 1000 kilograms per meter cubed. I've also calculated the weight density shown here. And in the question, we're informed that the losses, denoted as HF, equate to 2% of the potential head. Potential head, of course, is H1. So the calculation is 0.02, that's the 2%, multiplied by H1 shown above. So the loss in terms of head is 6.928 meters. Question 4a, solution continued. Here's the solution for part 1, determining the pressure P1 at station 1. Station 1 shown here, it's the inlet to the pipe. So pressure P1 is rho g times the h. Now the h in this case is 30 meters, the head of fluid in the reservoir. So P1 is the weight density, 9,810 newtons per meter cubed, multiplied by 30. So there's our pressure, pascals here. I've also stated it in bar purely for reference. So that's the pressure at the entrance to the pipe. Question 4a, solution continued. Here's part 2. Here we have to calculate the output velocity, V2, for the outlet pipe. So here's Bernoulli's equation, including frictional losses. So on the left-hand side here, the term P1 upon rho g, that's equivalent to a head of 30 meters. The question clearly states there's no velocity at the inlet, so ignore this term. There is initial H1. We calculate that as 346.4 meters. So we've got two terms on the left-hand side here. On the right-hand side, there is no pressure at the outlet because the outlet of the nozzle is into atmospheric pressure, so that's 0 gauge pressure. We're trying to calculate V2, so we have this term here, V2 squared divided by 2g, so denominator is 2 times 9.81. We considered our datum to be at the outlet nozzle, so H2 will be 0. And of course we do have frictional losses in this case, calculated that previously at 6.928 meters. So we evaluate on the left hand side, simplify on the right hand side, and then transposing for V2, we subtract the 6.928 head from both sides of the equation, and then we multiply throughout by 19.62. The square root in both sides, we find the velocity V2 is 85.14 meters per second to 2 decimal places. Question 4a, solution continued. Part 3, we're asked to calculate the output velocity, V2, if the outlet pipe's diameter is now increased to 2 meters. Note from the question, the initial outlet nozzle diameter was 600 millimeters. So what I've done here is essentially use the continuity equation, A1V1 is equal to A2V2. So assuming the same flow rate between the 0.6 meter outlet and the 2 meter outlet. On the next slide, I'll just replace the A1 with pi d1 squared divided by 4. On the right hand side, I've replaced A2 with pi d2 squared divided by 4. The pi and the 4 cancels both sides to leave us with this equation, which I then simply rearrange for V2. I'll let you work through the solution at your own pace, but you find that V2 is 7.663 meters per second, and I've also shown V2 in terms of kilometers per hour. And purely for your reference, here's the unity bracket calculation, converting our speed in meters per second into kilometers per hour. And here's question 4a, alternative solution to part 3. We're calculating the output velocity V2, and the outlet pipe diameter is increased to 2 meters. The only difference in this solution is I actually calculated flow rate Q dot. To do that, I needed to calculate the area A2 for the 0.6 meter diameter pipe, area shown here in terms of pi meter squared. Here's the actual Q dot calculation, flow rate in meters cubed per second. Then I calculate the area A2 based on the new diameter of 2 meters. That evaluates to pi meters squared. Then by rearranging the flow rate equation, velocity V2 in the 2 meter diameter pipe, I can calculate the velocity. That's an alternative solution to part 3, which I generally find technician students prefer. And finally, here's question 4a. This was the actual classroom solution worked through with the students. Very similar approach here, calculating the pressure P1 at entry to the pipe, then again referring to Bernoulli's equation, eliminating the terms that are not relevant to the problem, but in this case we've transposed the equation algebraically to calculate V2. Of course, the same values on the previous slide. And again we went on to find the value of V2 if we have an increase from the 0.6 meter diameter pipe to the 2 meter diameter pipe. But the classroom solution is just for reference. Finally, I will leave you with some first tutorial questions related to Bernoulli's and continuity equations. Here's question 1b through to 3b. Answers are shown in these square brackets on the right hand side. I encourage you to start the presentation and attempt these questions, but you are left to develop your own solutions to these questions. Question 4b, question 5b. Again, answers shown in the bracket on the right hand side. Here's the bibliography on which this presentation was based. And I hope this presentation has been of use to you, and as always, thank you for viewing.